So the last part of the neural network basic, I would like to show you a more complex example. So here's the example. We have x and y and a target. So basically, the y, right, you can think that is x1, x2 because the target is the actual y. Okay, so you can see that the figure looks like this. We have x1, we have x2, and the target is y. And apparently, this data set is not linear separatable, right? Just as the example we show you in SVM, right? So we'd like to show you how neural network can perform a prediction, which can predict the class of such kind of data. Okay. So the first thing is that we would like to create, again, it is a sequential model, but we have 6 different layers, actually 7, okay? As we mentioned before, you should always apply normalization before you use neural network, but since the data right here looks good, because the range of x1 and x2, they look similar, right? So we simply just ignore the normalization. So here is the structure of this neural network. Okay, for the first one, okay, we have a dense layer. So we have 3 different neurons, which is H1, H2, and H3. And you can, so after that, we have an activation function there, which is a ReLU. You can write it in this way, or you can write ReLU in the dense layer as a parameter. But I would like to show you how activation function works. So I write it separately. So the second layer, L2, which is the activation function layer. So after that, we have another dense layer which has 3 neurons, which is layer 3, and we have another activation function, layer 4, and another dense layer, 3 neurons, layer 5, and another activation function layer as layer 6. And after that, we have the last y, which is the only 1 neuron. Okay, that is our neural network. Okay, as you can see, it is very complex because it has several different layers, has multiple neurons, okay, and has nonlinear activation function. Okay, and again, since it is classification problem, so the loss function we select right here should not be MAE or MSE. So we use binary cross entropy since we have only 2 different classes, 1 or 0, right? In this figure, that is purple points or yellow points. And again, you can use some optimizer. Adam, again, learning rate 0.001. Okay, and here that is a matrix. Since it is a little bit difficult for us to understand the value of cross entropy, so for classification problem, usually we use accuracy as our matrix. Okay, and again, for the fit function, we provide x and y. Again, we run 200 epochs, and the validation data set is 10%. And in total, we need 20 seconds to perform the training. Okay, and again, here's the summary. Okay, although it has several different layers, but for activation, we don't need to train anything, right? So for the dense layer, okay, it has corresponding parameters should be trained. And after that, okay, here's the result. Originally, we have 450 data points, right? But right here, we don't have testing data set. So all of the 450 data set will be used for training. But we have 10% of data. So train, validate, state and the test, right? So we don't have testing data set. So 90% for training and 10% for testing. And we have 450 data points, so that would be 45, and that is 405 data point will be used for training. So here, after training, okay, since we have 200 epochs, so after each epoch we will calculate the accuracy, okay? So we have 405 data points, okay? They are either yellow or purple, right? So we use the, so for the very first epoch, okay, we have some theta 0, right? They are randomly selected from normal distribution. So ideally, the performance should be very bad. Okay, so at that point, for the training data set, only maybe 50% of the data should be are correctly classified. But we know that is that make no sense, because those theta 0 is some random weight. Okay, so we can see that after 75 epoch, okay, the classification accuracy gradually increase. So that means those weights are gradually trend. So we can find the minima loss, which is the I think that is the cross entropy value. Okay, that's the So you can see that after maybe after 150 epoch, and you can see that the training data accuracy becomes maybe 99% or even 100%. And then you can see that for the validation, these 45 validation data set can be correctly classified. And maybe that is, I don't know, maybe that's 95%, and maybe that is 99%, and so on and so forth. Okay, so maybe we can stop at 150 epochs. Not, you don't have to spend time to 200%, 200 epochs. Okay, so that is how we get all those weights. Okay, and we like to plot the value. Okay, that is x1 and that is x2, right? We have two different sets of data, and as you can see that I would like to draw L1. That means we can copy this. Okay, the L1 means after x1 and x2, after performing this weight, I would like to show h1, h2, and h3. But since it is a it is only a plan, right? So that is h1, that is h2. There's another h3, but I did not show it because it would be a little bit complex to observe the data. So I only show you the h1 value and h2 value. And as you can see that you simply just take a look at this part, and that means we have a red one, okay, the W1T times the original X, and after that we get the blue edge, right? And that is the size is something like this. the size is sorry. The size should be something like this. All right. So think about this. We talk about how to transform data from higher dimension to lower dimension to low dimension by using PCA, right? Think about that. We use matrix to transform the original data set from the original space to another PC space, right? The equation is exactly the same as this one. We use the original space, which has only two dimensions, which is x1 and x2, and we use a magic function, or say a matrix, to transform the original two-dimension data to three-dimension. And this three-dimension data is h1, h2, and h3. So basically, if you take a look at this part of the neural network, it can be viewed as a data transformation from some dimension to another space. So in this case, although we only show h1 and h2, but you can see that it's a transformation. It's a linear transformation because the W1T, it is just some linear transformation. Okay, and as you can see that if we perform layer 2 on layer 1, which means for every h1, h2, and h3, we perform ReLU, which means if the value of h1, h2, and h3 is larger than 0, and we keep it. If the value of h1, h2, and h3 is less than 0, and it becomes 0. So we can simply just draw a line, something like this. So for data points in this section would be the same right here if you perform ReLU. So for data point right here, okay, because its h1 value is negative, right, but its h2 value is positive, so this data point will become somewhere here, because after ReLU, its h1 value will become 0, and its h2 value, which is positive, will still be positive, the original value. And for all the data points right here, both their h1 value and h2 value are negative values, so they will become 0, 0, and so on and so forth. So after such kind of nonlinear transformation, the space of h1, h2, and h3 will become this. Will become this. It looks weird, but that is how neural network change or transform your data in different spaces. So that is layer 2. And after layer 3, layer 3 is still right here. Layer 3 is somewhere right here, right? Again, that is edge, right? And we have another transformation. So basically, from layer 2 to layer 3, it is just some transformation, linear transformation. Okay, because we did not show you the third axis, so it looks a little bit weird, but that is how we transform the data point from the previous layer to the next layer by using some weight, which can perform linear transformation in different spaces. Okay, and again, after that is layer 4, so that is a redo again. So we will squeeze the data point to 0 point or to the exit, something like that. The result is like this. So again and again. So finally, that is layer 6, and we can see that after linear transformation, after nonlinear transformation, we can change the original data to another space, which looks like this. And if you can simply just differentiate purple point and yellow point, and that means you can successfully perform classification with those different layers, and that is neural network. Okay, we stop right here because that is the last thing I will talk about. We will talk about several different concepts later about what if we have different layers, number of layers, what if we have different number of neurons, and what if we choose different types of activation function, and what if we don't use dense layer to describe the relationship. So that would be the topics of next week or 2 weeks later. But before we stop, we would like to show you something about orange. Okay, so let's take a look at the orange. Okay, I think that's good. So for orange, okay, you can always use a file. For example, we use iris data. So we have 4 different features and 1 categorical target. So in the previous homework or demonstration, we simply just, for example, we use the linear regression, okay, logit regression to perform classification, right? So here the accuracy is 97.3% right here. Okay, so if you want to use neural network in orange, which is quite simple as well, you simply just use the neural network widget. But the neural network provided by orange is very, I say, simple. Okay, because you take a look at this one. Okay, here's the configuration interface, right? So here you can set that neurons and hidden layers. So that means we want 2 additional hidden layers. Okay, so as for iris data set, okay, the input layer should have 4 neurons, right? Because it has 4 different features. You don't have to write 4 right here. Okay, you only need to write the number of neurons after the input layer. Okay, so we design a 2 hidden layer neural network. So the iris has only 1 target, right? So after this 100 neuron, it should has 1 additional dense layer, right? But you don't have to write it. Okay, you simply just write hidden number of neurons of your hidden layers. Okay, and you can select different activation function, as we mentioned. ReLU, hyperbolic tangent, and sigmoid, sometimes they are popular activation function, but we will talk about the difference of them later. Okay, so the identity right here is that we don't you do not perform any activation function. Okay, so solver right here is Adam, and of course that's we will talk about the optimizer later. Okay, so that is okay. So the maximum number of iteration, that means how many different epochs you want to use. So that is a very basic configuration of a neural network, but it takes some time to perform training because you need some time to perform gradient descent. Okay, after that you can see that the neural network is not necessary when, okay, logistic regression looks better, but it really depends on you to design different neural networks. Okay, so you can basically for students, you should try different settings. For example, you can use neural network like this. That means you have multiple layers. Okay, you have multiple layers, but you have a few neurons in each layer. Okay, and you can see that after that, you can see that the performance become bad. Is better than the previous one, right? Because as we mentioned before, when you have multiple layers and multiple neurons, that means you can. Okay, let's go back to this one. Okay, when you have multiple neurons or multiple layers, okay, that means you have more possibility to calculate its corresponding y, right? Because you can, as we mentioned, as we shown you before, like this one, okay. Since your data might be nonlinear, right? If you have more neurons or more layers, that means that the shape, the final shape of your boundary line or your fitting line would be more complex. So it's really depend on how complex your model is. Because if your model is more complex, then it is you have more chance to have higher accuracy or lower MSE value. Okay, so it takes time for you to develop different layers or different neurons. You have to try. Okay, but we will teach you how to try those different parameters later. Okay, so we stop right here, and next week we'll talk about some other structure of neural network.